All right. Okay, so if you haven't yet turned in the homework for 11 through 18, make sure you do that soon for late credit, okay? Now, we're entering the third part of the class. And by the way, homework 1 will be graded by the withdrawal deadline, okay? Gotta make sure of that. But the third part of the class will go from lessons 19 to 23. And that's going to cover more continuous probability, especially the normal distribution, which is extremely important in statistics. It's the most important category of bell curves. Then during the week of the withdrawal deadline, then we'll discuss the homework on these 2 sessions here. And the homework due date is the day before the withdrawal deadline. So it's actually, it's going to be Thursday, October 22nd. And I better have 1 graded by then, right? At least. But Thursday, October 22nd is the due date for homework 3. And then the withdrawal deadline is Friday, October 23rd. All right. Any general questions? Any general questions? Okay, so we are recording. All right. So let's get to it then.
We're going to start talking about continuous probability. Well, I mean, we've been talking about these normal bell curves, and they were examples of continuous probability, but now we're going to officially enter the realm of continuous probability. How do we work with probabilities when the possible outcomes have no gaps between them? Bear in mind that before, with discrete probability, when we looked at the result of a die, 1, 2, 3, 4, 5, 6, these were nicely spaced out possible values for x, the result of one die. The possible values of x were nice and discrete. You could easily list them, organize them nicely. However, they did not fall on a continuum. In continuous probability, we allow for values like 1.1 or 1.01. Now, in lesson 19, we're going to start with continuous uniform distributions, which are the most basic category of continuous distributions. And we're going to discuss the relationship between probability and area. Basically, in pictures like these, there's a direct relationship between areas and probabilities. In fact, areas are probabilities. And we can talk about that even in the context of discrete probability. While we're at it, let's review these examples from discrete probability. So in part A, we'll discuss probability histograms and ideas of area. Before, we could use probability histograms like these to describe discrete probability distributions, such as the one for the result of one die rule. And this is an example of a discrete uniform distribution because the probability for each possible face was the same. It was 1/6. So for example, what's the probability of getting a 3 on one die? Well, it corresponds to the area of the corresponding bar. And how do we get the area of this corresponding bar? Well, area is given by, you know the formula, area of a rectangle is given by base times height. Here, the base, or the width here, is 1 unit. We're going to assume that each of these bars has width 1 unit. The height is the probability, 1/6. And therefore, the area of this bar in here, the area of the bar inside here, is going to be 1 times 1/6, or 1/6. That's the probability of getting a 3. The probability of getting a 3 on one die is 1/6, which is the area of this corresponding bar. Now, these are probabilities for individual outcomes. The probability of getting a 1 is 1/6. The probability of getting a 2 is 1/6. The probability of getting a 3, as we saw, was 1/6, and so forth. But in general, we can also talk about the probabilities of events corresponding to areas. So again, if each bar has a width of 1 unit, then the probability of an event equals the total area of all the bars corresponding to that event. So for example, what's the probability of getting an odd number? Well, what are the odd numbers? The odd numbers on a die are 1, 3, and 5. The corresponding probabilities or areas are 1/6, 1/6, and 1/6. Again, discrete uniform, these probabilities are equal. The probability of getting an odd number is the sum of these probabilities. 1/6 plus 1/6 plus 1/6, that's 3/6 or 1/2, which is the total area of all the shaded bars in this figure. The probability of getting an odd number was P of 1 plus P of 3 plus P of 5, 3/6 or 1/2. Okay. Now, we're going to go from bars with flat tops to more general curves. We talked about normal bell curves before, but now we're going to talk about flat tops. Okay, flat tops, just guys like these. These are continuous uniform distributions. But still, I'll refer back to these bell curves for reference. In part B, we'll talk about probability density functions. When working with a continuous distribution, we use a probability density curve, such as this bell curve over here, or this flat top guy over here, instead of a histogram. The curve here is called a probability density function, or it represents a probability density function. So here are properties of a probability density curve and its density function. The area between a probability density curve and the x-axis is 1. So the area between this bell curve and the x-axis is 1. The area between the flat top and the x-axis will be 1, all right? Again, the area here will correspond to total probability, which is 1. If the probability density function is f, in general, we can call a function f, then f of x is greater than or equal to 0, meaning it's non-negative for all real values of x. This means that the density curve never falls below the x-axis. So for example, this bell curve here would never fall below the x-axis. That never happens. That never ever happens. The bell curve always has to stay above the x-axis. In principle, you can bounce off the x-axis, but you never fall below the x-axis. Okay, so our most basic continuous distribution is the continuous distribution of this type, the continuous uniform 0-1 distribution. The continuous uniform distribution on this interval of values. And in fact, random number generators generally have this type of distribution. So you often find this in software packages or on calculators. Random number generators often give values for x, where x has as its distribution a continuous uniform distribution on this interval from 0 to 1. This distribution is perhaps the most basic continuous distribution, even more so than the bell curves. The value of x in this case can be any real number between 0 and 1. And in fact, on Excel, there is actually a function, the rand function, which spits out generates or iterates from this distribution. So rand here, this is the description on Excel. Rand returns an evenly distributed random real number greater than or equal to 0 and less than 1. Basically between 0 and 1. A new random real number is returned every time the worksheet is calculated. Now, these random numbers are really pseudo-random numbers. They come from an algorithm. In this case, the Mersenne twister algorithm. I can't really describe that to you, but this is a link to a Wikipedia article on it. But for all practical purposes, we can think of them as random because the algorithm is so unpredictable in its nature. So in Microsoft Excel, the command is, well, equals RAND, and then you put a pair of parentheses. And here is a random number between 0 and 1 from that continuous distribution. We could have a list of 10 of them. So here we have a list of 10 random numbers between 0 and 1. Again, many scientific calculators will spit out these kinds of values from this distribution, a continuous uniform 0-1 distribution. Now, the density curve is flat, like this. The probability density function f is given by the rule f of x equals 1, where x is a real number between 0 and 1. So here, x can take on values between 0 and 1. The height is 1. The area of this square, well, it's a 1 by 1 square. The area under this flat top curve is 1, and that represents total probability, 1. The area of the total rectangle is 1. For any continuous distribution, the probability of any particular value is 0. So for example, let's say that 0.3 is over here. So 0.3 is over here. Okay. But if you look at the corresponding area, really, it's just a line segment. And what's the area of a line segment? The area of a line segment is just 0. So technically, the probability that x takes on exactly the value of 0.3 is 0, which might seem a bit contradictory because we're claiming that 0.3 is a possible value of x. It's a number between 0 and 1. It's a number that could be spit out by this Excel spreadsheet. So there's a bit of a paradox here, and it really stems from calculus. There are infinitely many possible values between 0 and 1, and they're splitting up this total probability of 1 among these infinitely many values. So that's really a calculus idea. Even though the probability of each individual value is 0, we're still saying that values such as 0.3 are possible. And I realize this may seem contradictory from when we talked about discrete probabilities. Again, it's a calculus idea. In fact, when you look back at the description on Excel, so technically the rand function could in principle spit out a 0, but it cannot spit out a 1. But we don't have to worry about that because technically the probability of getting exactly a 0 or exactly a 1 is 0 anyway. So here, when I was defining this distribution, I said that x could be any real number between 0 and 1 inclusive. Really, it didn't matter whether we had the bars here or not, because the probability of getting exactly a 0 is 0, and the probability of getting exactly a 1 is 0. So we don't even have to worry about the bars here, whether they're there or not. So again, for any continuous distribution, the probability of any particular value is 0. For example, the probability of a 0.3 is 0. That's the area of this line segment. In fact, it's the area of any line segment, including the ones at 0 and 1. And yet, we can say that these various values are possible. But how do we assign positive probabilities then? How do we assign positive probabilities? It is only possible to assign a positive probability to an interval of values for x. So for example, well, the probability of getting something between 0 and 1 is 1. We can assign positive probabilities to areas of, say, rectangles or bars like these. But these bars, maybe rectangles or squares, will correspond to intervals of values. Here, the area of this bar is the probability of getting between a 0.3 and whatever this is, maybe a 0.5. For continuous uniform distribution on an interval, the probability mass is spread out evenly on that interval. So pieces on the interval that have equal width will correspond to equal probabilities. So for example, let's say that the interval here is the same width as the interval here, from here to here. Then for a continuous uniform distribution, the area of this bar here will equal the area of this bar here, and the corresponding probabilities are equal. And that's true for continuous uniform distributions if you're talking about intervals that are between 0 and 1. We're going to talk about particular calculations and computations with this distribution in the next lesson.
All right, any questions? Any questions? All right. Yeah, because some people get creeped out by this. If you're taking calculus, it's more helpful. All right, let's proceed. Feel free to chat questions. I guess a little theoretical.
Hi, everyone. We're continuing with continuous uniform distributions. In particular, this basic distribution, the continuous uniform distribution on this interval from 0 to 1. All right. Now, again, remember that we relate areas with probabilities. That's a key theme of this lesson, and in fact, for much of this class. So let's say that x has as its distribution this distribution, a continuous uniform distribution on this interval from 0 to 1. So x can take on any real value between 0 and 1. Okay, then let's find the probability that x can be some value between 0.2 and 0.7. All right. Turns out to be 0.5. Now, why is that? Well, we look at the corresponding area. So from 0.2 to 0.7, what is the width from 0.2 to 0.7? Well, 0.7 minus 0.2 is 0.5. So 0.5 is the width, 1 is the height. Area of a rectangle, like this gray shaded rectangle, is base times height. 0.5 times 1 is 0.5. That's the area of this gray shaded rectangle. Therefore, that's the probability that we're looking for. The probability that x is between 0.2 and 0.7, if it's generated like so, that probability is 0.5. So in other words, this gray shaded rectangle makes up 1/2 of this square. Again, areas correspond to probabilities. The shaded region is a rectangle with base 0.5 or width 0.5 and height 1. I know it's a little confusing because before, widths or bases would be 1 and then the height would be the probability. Here, it's kind of flip-flopped. Here, the width basically gives us the probability and the height is 1. Okay, now you might be asking, what happens if instead of is less than, we have is less than or equal to, but it turns out not to matter. So the probability here for all three of these probabilities have the same probability as before. It's going to be 0.5 for all of these, because it doesn't matter whether you include the actual line segment here or not. It doesn't matter if you include the actual line segment here or not. The area here is still 0.5, regardless of the actual boundaries, whether or not they're included or not. And that's because the probability that x is exactly 0.2 is 0. The area of this line segment is 0. Likewise, the probability that x is exactly 0.7 is also 0. The area of this line segment over to the right is 0. So for continuous distributions, again, it does not matter. It does not matter whether you have is less than or is less than or equal to. So as far as these kinds of probabilities go, it doesn't matter whether you have bars underneath here or not. It does matter that this number, the 0.7, is bigger than this number over here, the 0.2. If these were flip-flopped, or if you were to reverse the symbols, then the answer would be 0. Okay. Now in general, if instead of 0.2 to 0.7, what if we have some other interval? Let's say this interval from x1 to x2. Probabilities for continuous, uniform, 0-1 distributions. Assume that x has as its distribution this distribution, uniform 0-1. So the probability density curve is just this flat line segment up here with height 1. Okay, now we have a total area of 1 inside this square, this 1 by 1 square, right? But let's say that we want to know the probability that x falls between x sub 1 and x sub 2. Well, again, the area of a rectangle is given by base times height. The height is 1, which means that the area is given by just the width, or the base here, which is x sub 2 minus x sub 1, the width of this subinterval over here. So the probability that this random variable is between x sub 1 and x sub 2, I'm assuming that x1 is no more than x2. This probability is going to be the larger value minus the smaller value. And of course, both these values have to be between 0 and 1. The probability you get something between 30 and 50, say, is going to be 0. There's nothing out here, really. Okay, so the probability that x takes on a value between, for example, 0.2 to 0.7, that's going to be 0.7 minus 0.2, or 0.5. Okay, so now let's say that instead of the interval from 0 to 1, our continuous uniform distribution goes from 30 to 50, or from 2,000 to 3,000, in general, from A to B, assuming that A is less than B. So how do we deal with these continuous uniform distributions on a more general interval? Maybe not from 0 to 1, but from A to B, where A and B are real numbers and A is less than B. Okay, so X has as its distribution a uniform distribution, a continuous uniform distribution on A to B, meaning X can be any value between A and B. All right, well, let's take a look at this picture. Now remember that total probability is 1. The total area of the rectangle here has to be 1. Now, if we're looking at possible values of X being between A and B uniformly, then the width or base of this rectangle is given by B minus A. That's the width or base of this rectangle. The height of this rectangle is given by 1 over B minus A, the reciprocal. The reason being that we need this times this over here. I need, once again, this times this over here, that product to equal 1. So the height of this flat top, the density function, must be given by this value over here, the reciprocal of the width. Okay. Now let's say that we want to know the probability that X will be between the values X sub 1 and X sub 2, where again, these two values are between A and B, and X sub 1 is, let's say, less than X sub 2. Then the probability that X, which has this distribution, continuous uniform from A to B, the probability that X is between X sub 1 and X sub 2 is given by this fraction over here. And there are two ways of looking at that. One way is to look at it in terms of areas. So the area of a rectangle is given by base times height. The base, or the width, is given by the width of this subinterval, X sub 2 minus X sub 1. That's the width or base of this gray rectangle. The width of this subinterval is X sub 2 minus X sub 1. The height is given by 1 over B minus A, the reciprocal of the total width of this rectangle. Well, base times height. Base is X sub 2 minus X sub 1. That's this over here. The height is 1 over B minus A. The area of a rectangle is base times height. Base times height. This fraction, X sub 2 minus X sub 1 over, I'll use a different color now, B minus A. So basically, it's the width of this subinterval for this gray rectangle over the total width from A to B. And in fact, that's a second easier way of looking at it. Look at this fraction over here. What is the area of this rectangle? What proportion of 1 is the area of this gray rectangle? Well, since we have a common height all the way throughout, the proportion that this gray rectangle makes of the total rectangle over here is going to be the proportion of this red subinterval to this purple total interval. So for example, if this red subinterval, the base of this rectangle, is 1/2 of the total interval from A to B, then the area here, the gray area, is 1/2 of the total area. And the probability that X is between these two numbers is 1/2. So again, a simpler way of looking at this is that the probability that a uniform AB random variable lies between X1 and X2, it's equal to the proportion, the ratio of this smaller width to this larger width. It's a proportion. So if this width is half of the total width, the probability is 1/2. If it's a third, the probability is a third, and so forth. Now, in our next example, we're going to actively apply this formula. On a test, this formula will be given. So let's say that we have a continuous uniform distribution on this interval from 2 to 10. So A is 2 and B is 10. These are the endpoints of our larger interval. 2 here and 10 here. First of all, I'd like to go to Excel and show you how we can generate some random variables with this distribution. And actually, Excel does require on a formula technique. Now, first of all, you may remember from the last lesson that to get a random number between 0 and 1, this is for a uniform distribution, 0, 1, where X takes on a value from this distribution. we would put equals rand and then a pair of parentheses. In fact, we can take 3 random generates from this distribution. And here we have 3 random numbers between 0 and 1, this continuous uniform distribution. So for example, lower numbers in the interval are no more likely than higher numbers, or vice versa. Now, what if instead of a uniform distribution between 0 and 1, let's say we wanted a uniform distribution between 0 and 8. So we get random numbers between 0 and 8. Or again, we have a flat top. It's a continuous uniform distribution. The width of this interval is 8. So what we do is we would use equals rand, parentheses. So this would give us a continuous uniform 0, 1 random variable, a value for that. But then if we wanted something from a 0, 8 interval, we would take this and multiply it by 8. So here, this number here would be a random value from a uniform 0, 8 distribution. It's about 6.2. We can take 3 of these. So here we have 3 random values from this uniform 0, 8 distribution. Again, there's no favorability towards lower values, higher values, or middle values. But wait a minute, what if we want random numbers between 2 and 10? So basically, we want to lift up this distribution by 2 units. We want random variables from a uniform 2, 10 distribution. Well, we take 0, 1 random variates, those values, multiply by 8 so that the width is 8. But since the bottom number is 2, since A is 2, we add 2. So we basically lift up all these values by 2 units. And here we get a value between between 2 and 10. We can do 3 of these, let's say. Again, here we have 3 random values from this distribution, a continuous uniform distribution from 2 to 10. It required some hacking in Excel. There's not a super clean formula for this, but you basically exploit the basic rand function that we used before for the classic continuous uniform 0, 1 distribution. So if your scientific calculator or Excel or your program can produce these kinds of generates, if it can work with this basic distribution, then you should be able to manipulate this to get continuous uniform generates from more general continuous uniform distributions, whatever A and B are. Again, you multiply by the width to get these, and you add by A, the minimum value, to get these. Okay. Anyway, that's the distribution we've been talking about, a continuous uniform distribution from 2 to 10. But let's say we want to know the probability that a random variable from this distribution will take on a value between 4 and 7. Basically, what's the probability that this value was going to be between 4 and 7? Okay, we can use this formula where x sub 1 is 4. That's the minimum value that we're interested in. X sub 2 is 7. That's the maximum value that we're interested in. Right? A is 2, B is 10. That was fixed in the distribution. So we want to know what proportion does 4 to 7 make out of 2 to 10? Well, x sub 2 minus x sub 1, 7 minus 4 is 3. That's the width of this gray box over here. Over, well, what's the width of the bigger box over here? It's b minus a. 10 minus 2, or 8. 10 minus 2 is 8. So the probability that x is going to fall between 4 and 7 is going to be 3/8, or 0.375. That's the proportion of area that this gray shaded box makes out of this big box over here. But because we have a flat top, we can just look at the numbers down here. 4 to 7, that's a width of 3 units. 2 to 10, that's a width of 8 units. 3 out of 8, that's the proportion, 3 out of 8. So the probability that x, which is from this distribution, the probability that x is between 4 and 7 is 3 out of 8. All right, so that takes care of continuous uniform distributions. Next, we're going to go back to our favorite shapes these bell curves. Next time.
Okay, any questions? Because although we're still sticking with continuous distributions, we're going to shift gears a bit, all right? Any questions? Any questions? All right. One more, then I have a little video to show you. I emailed it to you.
Hi, everyone. We're continuing with continuous probability distributions, and we're now going to come to these bell curves. And in particular, we're going to start with our famous bell curve, the standard normal distribution, or the standard normal density curve. First of all, you might be wondering why we call these density curves. Well, here's the idea. Let's say you have the state of New Jersey, right? The state of New Jersey has a much higher population density than the state of Wyoming. So, for example, if you take a square mile in the state of New Jersey, it probably has a lot more people in it than a square mile in the state of Wyoming. Well, similarly, if you look at this standard normal density curve, okay, then you can see that the probability mass is bunched up near the center, the mean, which is 0. And if you take an interval from, say, here to here, okay, versus an interval of the same width even, from, say, here to here, okay, maybe these intervals are the same width, but we have much more probability mass here near the mean than away from the mean. So we have a greater bunching up, a greater probability density near 0, the mean of the standard normal. Whereas for our old school continuous distribution, from 0 to 1, let's say, it was nice and evenly spread out. The probability mass was nice and evenly spread out between 0 and 1, or in general, from A to B. So before, we talked about these continuous uniform distributions, especially the one from 0 to 1. Now we're going to talk about this standard normal distribution. Now its parameters are also 0 and 1, but the 0 and the 1 here are not endpoints the way they were before for the continuous uniform. Here, the 0 will be the mean, and the 1 will be the standard deviation. So 0 and 1 mean something different here as opposed to here. All right, lesson 20 on the standard normal distribution, our favorite normal distribution, which tables have been written about, and we'll talk about those. What do z-scores tell us about normal distributions? All right, so there's a direct relationship between these standard normal random variates and z-scores. All right, what is the standard normal distribution? The standard normal distribution is sometimes called the z-distribution because we associate values of this standard normal distribution with z-scores in many contexts. The standard normal distribution is the normal distribution with mean 0 and standard deviation 1. So in notation, we often use z to indicate a standard normal random variate. Z has as its distribution a normal distribution with mean mu equals 0 and standard deviation sigma equals 1. 1 unit. Remember, for the standard normal distribution, there are no specialized units like pounds or feet or yards. The idea is that we can apply the standard normal distribution in a variety of settings. We assume that z is a standard normal random variable. So when you hear about a z-score, we usually assume it comes from a standard normal, though not always. All right, so what are some properties of normal distributions in general, but especially for the standard normal? I'll bring up my copy over here. All right, so what are some properties of standard normal distributions and normal distributions in general? First of all, they are continuous. They are continuous. They can take on a continuum of values. So for example, in the standard normal, you can have values of 0, 1, 0.1, 0.11, 0.111. Any real number can be a standard normal value. They're continuous distributions. Also, a normal random variable can take on any real number as a value. Any real number is possible. The density curve is bell-shaped. It's the classic kind of bell shape, although there are others, as we'll see later in the semester. the density curve is symmetric about the mean. Okay, so we have this mean line over here, and the density curve is symmetric about that mean line. So probabilities here correspond to probabilities over here. The standard deviation is the distance between the mean line and either inflection point. I'll go to my nicer pictures down here. These are produced by Mathematica. Okay, so in general, for a general normal distribution, the mean, if you look at this center line here, the mean corresponds to this hilltop. The standard deviation, sigma, is the distance between the mean line and either inflection point. Remember that an inflection point, okay, an inflection point is where the density curve changes from concave up to concave down, or vice versa. So over here, at this inflection point, these are points you see in calculus. This is a point where the curve, the density curve, goes from going concave down to concave up in terms of the way it curves. For this inflection point, we're going from concave up to concave down. Again, one standard deviation is the distance between the mean line and either inflection point. Now, this knowledge is not absolutely essential for the homework, but it's helpful if you want to draw good pictures. Also, the tails of the curve fall off rapidly in terms of standard deviations. Remember the empirical rule. Remember the empirical rule. The empirical rule went 68, 95, 99.7%. 68% of the data, let's say, in normal data sets, 68% of the data, roughly, would be within one standard deviation of the mean. About 95% would be within two standard deviations of the mean. That would be like a usual range of values. And about 99.7%, almost everything, would be within three standard deviations. Basically, you're not going to have too much too far out to the right or to the left of the mean. You're going to have a lot of density close to the mean. It's bunched up there. The probability mass is bunched up near the mean. So that was the basis for the empirical rule. The relationship between that and the empirical rule. Again, for a standard normal distribution, the picture is exactly the same, except that we know that the mean mu is 0 and the standard dev is 1. Sigma is 1. All right. So that's a review of some continuous distributions. We've discussed properties of normal distributions in general. And remember that the standard normal distribution is the normal distribution with mean 0 and standard deviation 1. No units, because we can apply this to anything, as it turns out. Next, we're going to do some actual computations with actual numbers, and we can even verify numbers like these. Oh, and before I go, in case you're curious what the equation is for this curve, this standard normal probability density curve, is this over here. F of z equals this ugly thing over here. This indicates basically a kind of exponential decay over in the right tail and the left tail. There's a sharp falling off in the tails. In general, for mean mu and standard dev sigma, here's the formula for the function. And this is the graph of y equals ya, ya, ya. Bear in mind, this is just a special case of this, where x equals z, the mean mu is 0, and the standard deviation sigma is 1. The bad news is it looks like these. They're pretty ugly. The good news is you won't have to know these for homework. This is mostly if you're just curious. But again, we don't care so much about the equations of these curves. We don't care so much about the y-coordinates of these points. It's not the y-coordinates we care about. We care about areas, which means that we won't need these directly. We like to use tables or software. Okay, we'll do computations and we'll discuss tables and software in greater detail next time.
All right, and now I'm going to play the video. Some of you may have already seen it, but I'm going to play, just for fun, I'm going to play the cute little video. It's from the 1970s film Young Frankenstein, a great old comedy. Some of you have already seen this.
Hi Hi, everyone. I wanted to start this with this nice little Google Doodle for today. This is a tribute to public health workers and to researchers in the scientific community. Thank you. And I love the fact that there are a couple of bell curves up there. All right. Speaking of bell curves, the standard normal distribution, the most basic of bell curves. Remember that the standard normal distribution is the most basic normal distribution with mean 0 and standard deviation 1. Again, mean 0 over here, this mean line corresponding to this hilltop, and standard deviation 1, the distance between the mean line and either inflection point by symmetry. Now, the formula for this curve is given by this, but we don't worry about that. Don't worry, you won't have to use this. We're going to work with probabilities because we really care about areas. We don't care so much about y-coordinates. We care about areas. And those correspond to probabilities. Now, on the homework, I will give you hints. But you might be curious where these hints come from. For example, you might be curious in doing your own statistics. So I'll show you some online software, free online programs, and how you can use software like Excel to find out these hints. All right, so let's say that in example 1, software tells you that this probability, the probability that a standard normal random z, random variable, is less than negative 1.24, that this probability is about 0.1075. First of all, I want to show you a picture of what this means, and then show you how online programs and software can discover this hint for you. First of all, part A, sketch a figure clearly showing this fact and shade in the relevant region. All right, so I do want you to draw these kinds of basic pictures. And here is what I'd want you to do. Okay, so first of all, make sure that the negative 1.24 on the z-scale over here, all right, let me do this, the negative 1.24, okay, is to the left of 0. All right, so remember that the 0 is over here. Here's 0, corresponding to the mean line. At the very least, in addition to drawing a decent bell curve, please make sure that the negative 1.24 is to the left of 0. Now, the inflection point here does correspond to negative 1, but don't worry about that as much. The main thing is, I want you to show that negative 1.24 is to the left of 0. Okay. We're concerned about the probability that z is less than negative 1.24. This means that we're concerned about this area to the left of negative 1.24, because this corresponds to a left-tailed probability. And the software is telling us that this is about 0.1075. So I put the 0.1075 here, put an arrow here clearly indicating that I mean the area of this region, and that's that. Okay, we've answered part A, sketch a figure clearly showing this fact, and shade in the relevant region. This left-tail probability is about 10.75%. Now, you might be curious how you can get this information from free online software. Well, I'll show you. The probability that z is less than negative 1.24. How did we do this in the olden days? This is ztable.com, very appropriately named. And this basically gives us a table, which used to be in the old school textbooks. The textbooks still have these, where on an exam, students might be asked to pull these out and work with these tables, these print tables. And these z-tables would tell us these cumulative left-tail probabilities. So part A here was very well suited for that kind of issue, because this dealt with a left-tail probability, the probability that z was less than negative 1.24. Okay, so the z-table gives you the probabilities that are these left-tailed probabilities, these cumulative probabilities for a given z-score. Remember, we're curious about the case where the z-score here is negative 1.24, and we want to know this probability or area here. All right, well, in the left column, you look for negative 1.2, the integer part, and the tenths place, negative 1.2. And then for the hundredths place, you would look up north, up here, and here you have the 0.04. So here we have negative 1.24, okay? And you look inside, outward in. Negative 1.24. Don't you miss the olden days. All right, and look at this corresponding probability or area, 0.1075. So we're making the claim that this left tail probability here is 0.1075. All right, I'll go ahead and erase these marks, by the way. I need the eraser here. Okay, so erase this. Now, aside from tables, there are other ways you can find these things out. StatTrek, the normal distribution calculator. All right, standard score, let's put in negative, let's put in negative, blow this up, negative 1.24, all right. Okay, I pressed return. Okay, 0.107. All right, well, pretty close. We got 0.1075 over here. All right, this is saying 0.107. All right, and again, this corresponds to a standard distribution. Standard normal distribution, mean zero, standard dev 1. Okay. Also on my website, in the middle here, statistical calculators. See, this is tutorhomework.com. Standard normal distribution. Again, if you're looking for a left tail probability, all right. Okay, so we give it a z-value, negative 1.24. Click on this arrow, the probability we get, 0.1075, which verifies what we had in our table here. I've been skipping over the Excel spreadsheet here. I'll explain this. By the way, I didn't mention this before. Here's how you can generate some standard normal random variables. Norm.s.inv rand. It's a little complicated, but that's how you get a standard normal 0, 1 random variable. Okay, but I wanted to talk about this over here. Okay, so again, what's the probability that z is less than negative 1.24? All right, so it's the norm.dist command, normal distribution, negative 1.24. I'm interested in the left or cumulative probability for that z-score. Okay, I have the 0 and the 1 here because I'm dealing with a standard normal distribution. Okay, so I want mean 0, standard dev 1. And I put true here because I want a cumulative or left tail probability. If I put false, then I'm looking for the y coordinate of that point there on the curve, and I don't care about that. So I put true here, never false. Okay, so if I do that, equals norm.dist, negative 1.24, 0, 1, true. Right? So a 0.1075 roughly. All right, and that gives me the left tail probability. Okay, so basically I've been showing you a bunch of ways that you can figure out this hint. The picture, of course, was really critical here. First of all, to figure out what even the heck we were doing, right? But then we're going to use this picture to answer the other questions in example 1 in the next video.
All right, any questions? Any questions?
Hi, everyone.
Any questions? All right.
We're continuing with lesson 20 on the standard normal distribution. So last time we talked about this key hint here, the probability that a standard normal z is less than negative 1.24 is about 0.1075. And here was a nice picture illustrating that fact. Okay, now what we're going to do is, first of all, I want to use Excel to show you why this kind of makes sense from a simulation perspective. So here, remember that this command, norm.s.inv, allows us to generate standard normal random values. Let's do a whole bunch of these. In fact, imagine that we're doing like 1 million of these. What this probability statement is basically saying is that about 10.75% of the z-scores we're getting here will be less than negative 1.24. So about 11% of these, standard normal values, these random values, will be less than negative 1.24. Okay. Part B, find the probability that as a result of this hint, the probability that z is greater than negative 1.24, what is that? What is the probability that z is greater than negative 1.24? And again, remember, it doesn't matter whether there's a bar there or not. Okay, well, we want here a right tail probability. How do we get a right tail probability? Well, what's the total area under a probability density curve? It's 1. So in order to get the complementary probability, which is what this is, to get the complementary, whether there's a bar there or not, to get the complementary probability, we subtract from 1. So the probability that z is greater than negative 1.24 is 1 minus the probability that z is less than or equal to negative 1.24, but the bar doesn't matter. So it's basically 1 minus this probability over here, the complement. 1 minus 0.1075 is 0.8925. It's a big probability. And to get that, we shade all of that there. Okay, so we want to shade all of this over here to the right. 1 minus the 0.1075, the complement. Now on software, with the table, you just have to know that you take the 0.1075 that we got here and subtract from 1. But if you use things like, let's see, well, StatTrack also gives you the cumulative. If you go to the tutorhomework.com site, all right, it does give you a right tail option. Now, I hope that you know to subtract from 1 anyway, but if you forget, well, we're putting in negative 1.24. We want the right tail probability this time, and that's the big number, 0.8925. Remember, for the left tail, it was the small number, 0.1075. For the right tail, it's going to be 0.8925. So actually, that's small for the left tail. It's big for the right tail. Remember, negative 1.24 is out here. So the right tail is a big probability. All right, and for Excel, again, it would help to know that you subtract this from 1. And Excel expects you to know that. Equals 1 minus the entry in A2. Okay, Excel expects you to know that the right tail probability is the complement, 1 minus that. So Excel expects you to be smart. Okay. Now what about C? Find the probability that Z is greater than 1.24 based on the original picture from part A. How can we find that? Well, here's the deal. If negative 1.24 is over here, then by symmetry, would it make sense that positive 1.24 would be over here, right? Here's positive 1.24. And this bar here is symmetric to this bar over here. This region is symmetric to this shaded blue region over here. By symmetry, we get the same number. The 0.1075, which was the area over here, guess what? It's the same area over here. So the answer to C, by symmetry about the mean, the probability that Z is greater than 1.24 is the same as the probability that Z is less than negative 1.24. It's mirror images. It's mirror images. So where did I put the picture? Put up here. Okay, so these regions are mirror images of each other. The probabilities are the same. The areas are the same by symmetry. So 0.1075. Now again, most software like Excel would expect you to just know that, but well, tutorhomework.com, again, this is the really helpful one. Right tail for positive 1.24. Click on this arrow. From the Z value to the probability, we get that small probability again, 0.1075. And here the right tail picture is more consistent with what we'd expect. It's a small probability. Right. Now in the table, you would have to go to, well, one way to do it, go to positive 1.24, you get the positive 0.8925 as your probability, subtract that from 1. Because the 0.8925 is the cumulative all the way up to there. Okay, and you want that little tail to the right. Okay. So going on to example 2, what about an in-between probability? Software tells you that the probability that z is less than -1 is about 0.1587. You could have either Excel or websites demonstrate that for you. In fact, we can do that very quickly. Let's go over here. Let's do norm.dist -1, 0, 1, true, about 0.1587. 0.1587. If you go to tutor homework, the left tail for -1, 0.1587. If you go to the old school table, negative 1.00, well, it's right here. It's the very first entry, 0.1587. All right. In any case, that's the hint. Similarly, the probability that z is less than +1, that's a big probability, 0.8413. Okay, now, as a result of these, find the probability that a standard normal z is between -1 and +1. Sketch a figure clearly showing this and shade in the relevant region. Think about this. Try to draw a picture, try to figure out what's going on here, and what will we do with these probabilities? We want an in-between probability. So I'll kind of give you a hint. On tutorhomework.com, it's a middle probability. If you want to check your work, let's do that. Let's take middle. Okay, so we have middle here. So left, and there should be -1 comma. Oh, there we go. Yeah, so you would enter with a comma. So for the middle probability, you would enter -1, 1, and then click on that. And the probability is 0.6827. Now, does that sound familiar? That's about 68%. Do you remember 68% from somewhere? The empirical rule. 68, 95, 99.7. Basically, this is telling us that you have about 68% within one standard deviation of the mean if you have a normal distribution in general. And this verifies that. Guess what? If you go from -2 to 2, guess what? It's about 0.95, 95%. Anyway, back to the problem at hand. Find this middle probability. All right. So again, make sure that, okay, so I'll just go all the way to here, right? Make sure that the -1 is to the left of 0, because a lot of people make a mistake there. Make sure that the -1 is to the left of 0. 0 is this hilltop here, right? Where the hilltop is. 1 over here is to the right of the 0. We want this area, this in-between area inside here, the blue shaded region. So how do we get that? Well, we know that the area or probability to the left of -1 is 0.1587. So I'm indicating that that's basically this over here. 0.1587 is the area in white over here. Also, the probability that z is less than +1 is about 8413. Okay, that's the area or probability to the left of the +1. So here, I'm using arrows instead of shading because I think the arrows are a lot clearer. So we're talking about the left tail cumulative probabilities for -1, which is the 0.1587, and the left tail or cumulative probability, left tail probability for +1, which is the 0.8413. What do we do with these probabilities or areas? We subtract them to get the 0.6826, because the area I want, this blue shaded area, is going to be the area to the left of the +1, all of this, but I want to subtract that left tail area in white, the area to the left of the 0.1587. So I just want the stuff in the middle. I feel like a 5-year-old coloring in this picture. All right. So once again, to reiterate, I'll kind of clear this thing up here. What do we want? we want the total left tail probability all the way to the left of the 1, okay? But we want to subtract off the white probability, the area to the left of the -1, and then you get the middle piece that we want, 0.6826, which is consistent with the empirical rule. Okay, so that's how you deal with in-between probabilities. All right. Working with percentiles. This is the inverse problem. Before, I gave you or we asked software to intake z-scores and give us probabilities or areas. So that's what we were doing on this tutorhomework.com site so far, going from z-scores to probabilities. But what if we go backwards? What if we go backwards from probabilities back to z-scores? This is the notion of percentiles. Okay. So let's say that in example 3, let's say that software tells you that the 85th percentile of the z-distribution, the standard normal distribution, is about 1.04. Sketch a figure clearly showing this, shade in the relevant region, and write the corresponding probability statement. Now, first of all, what does that mean? Well, let's say that you score 1.04 standard deviations above the mean on a test. It's a huge lecture hall class, 1,000 students. You scored 1.04 standard deviations above the mean. And the scores are about normally distributed. Basically, what percent of the class have you beaten? You've beaten 85% of the class. All right. Well, now, that was the kind of question we asked earlier. The percentile question is now asking this. I want to know the 85th percentile, and we're going to show it's 1.04. The question here is, if you need to beat 85% of the class to get an A on this exam, let's say the scores are curved, the grades are curved, and your professor tells you that you have to beat 85% of the students in the class to get an A. How many standard deviations above the mean? Obviously, you have to beat the mean, which is the 50th percentile, basically. The mean is the median for a normal. How many standard deviations above the mean do you need to get in order to get an A? And we're claiming that it's going to be 1.04 standard deviations, but that's the cutoff for the A. All right, well, that's what this picture basically says. In order to beat 85% of the class, okay, in order for a random test to beat 85% of the scores in the class, in order to be at the 85th percentile, then you have to score about 1.04 standard deviations above the mean. Your z-score has to be about 1.04. And this is the corresponding probability statement. The probability that a standard normal z is less than 1.04, that probability is going to be about 0.85. So I gave you the 0.85, okay, and I gave you in the hint that 1.04 was the 85th percentile of the standard normal z distribution. So the software basically tells us what this is. Here's how software can tell us. Let's go to the tables in here. Now, we know that for the 85th percentile, we know that the z-score has to be positive because the 50th percentile corresponds to z equals 0 here, right? The 50th percentile corresponds to z equals 0. We know that the 85th percentile has to be a z-score that's positive. So in the old school tables, I want to look at the positive z-scores. And this time we look inside out. Where in here do we see about 85% or 0.85? Here we have, let's use this. Okay, so I see here 0.8485 over here, 0.8508 over here, 0.85 is in the middle somewhere between these two values, and I look up. Okay, I look up to the 0.03 and 0.04. More importantly, I look to the left at the 1.0. So the z-score I'm looking for is 1.03 to 4. So between 1.03 and 1.04. It looks like 1.04 is going to do a better job. 0.8508 is much closer to 0.85 than this is. Although the interpolation is not purely linear. Meaning you can't just go by who's closer all the time. Okay, but about 1.04. Well, you can see how the table is a bit awkward. Again, it's confirming this picture over here. But let's go to, how about, well, we can go to StatTrek. StatTrek works in reverse, okay? So 0.85 I want to put in the cumulative probability section, press return, and I see 1.04 basically here on tutorhomework.com. Okay, so this time we want a left tail probability. Percentiles correspond to left tails. So the 85th percentile, I want to know the z-score that gets 85% over here. In fact, this picture looks pretty good. I want a probability of 0.85. We want to go from probability to z-value. So I click on this arrow down here. It's about 1.04. Okay. On Excel, what is the 85th percentile of the z-distribution? In other words, find the z-score, z-star, such that the probability that a random standard normal z is less than that z-star score is about 0.85, equals norm.inv, it's the inverse problem. Given a probability, find the z-score. Given the left tail or cumulative probability, find the z-score. So 0.85, comma, we want a standard normal. Okay, well, to many decimal places, it rounds off to about 1.04. All right. So tutorhomework.com kind of puts it in a nutshell. I can either go from a z-value to a probability. So 1.04 gets us a probability of 0.85, or I can feed it a probability and I get the z-score, which inverts the previous problem. All right, so we've really talked a lot about the standard normal distribution. In the next lesson, we're going to talk about all normal distributions, and this is the key. The standard normal distribution is the key to all normal distributions in yards, feet, miles, light years, whatever. Until next time.
Any questions so far? Any questions? Any questions? All right, feel free to chat.
Hi, everyone. As a quick bonus topic, I want to explain why this command with the equal sign in front will give us standard, normal, random values. Okay, so the rand function equals rand with parentheses, okay? Let's get 6 of these. These 6 numbers correspond to probabilities for percentiles of the z-distribution. Now, to make sure these don't change, I'm going to go ahead and copy these and paste them as values so that these don't change ever again. Okay, so let's say I want to use these probabilities to get percentiles from the z. So equals norm.s.inv. And instead of putting rand parentheses again, I want to refer to column A. And I'll continue on. So this is telling me that about the 30th percentile from the standard normal z distribution is a z-score of about -0.51. The 45th percentile, roughly, gives us a z-score of about -0.14. Okay, well, that's a very low probability, very low z-score. The 94th percentile of the z-distribution is about 1.6. The 33rd percentile is about -0.43. It makes sense it's negative because remember, the 50th percentile is 0. So it makes sense that the 33rd percentile roughly is slightly negative. And the 68th percentile, we know that's going to be positive. It's about 0.48. So basically the randomness comes in this selection, this random selection of values from this continuous uniform distribution, which corresponds to probabilities. And these probabilities then lead to the corresponding percentiles of the z. The randomness comes in the selection of the probabilities. And we just pick up the corresponding percentiles from the standard normal.
Well, that's all. That was just a bonus topic there. Well, that's all really. All right, kind of a shorter. We're going to talk about more general normal distribution.
पिक्चर समझो जरा यहाँ पर थोड़ा सा इसका पिक्चर समझो यहाँ पर आपको क्लैरिटी मिलेगी
Calm down.
देखो क्या होता है आपने अभी थोड़ी देर पहले देखा कि सर अगर एक ग्लास स्लैब आपने यहाँ पर लगा दी या आपने लिख
All right. All right. Well, I'll stick around for any questions you might have. Yeah, that was kind of stressful, wasn't it? So you've done a lot of homework, so I think it's okay that today was kind of short. It's what 9? Yeah, wow, we're any kind of early, but that's okay. Anyone have any questions? Anyone have any questions? Okay, so people already starting off the homework. Okay, good. All right. So let's look at the homework. All right. What's There you go. That's just kind of stuck on my screen. All right. Yeah, I know. I guess it was from Zoom Annotate. I don't know how that got there. All right. So lesson 20. Oh, I see. I see. So yeah, students can draw my screen. That's a little scary. Okay. I see what you did. All right. Oh, number 4. So 24. Okay, software tells you that the 20th percentile of the z distribution is about negative 0.84. Sketch a figure clearly showing this, shade in the relevant region, write the corresponding probability statement. All right, so here's a standard normal. All right, 0 is about here. Okay, and where's negative 0.84? Is that to the left or to the right? Negative 0.84. It's going to be to the left. Negative 0.84. In fact, it's going to be pretty close to the inflection point. The inflection point here is going to be corresponding to negative 1. So it's pretty close to the inflection point. All right, so we have here's the negative 0.84. All right. Software tells us that the 20th percentile is about that. So that means that this here is going to have a probability mass of 0.2. Right. For all this in here. Shade in the relevant region. It's this over here. We're claiming that the probability that a random standard normal z is less than negative 0.84 is about 0.2, or 0.20 if you wish. Write the corresponding probability statement. All right, well, the probability that z, remember we tend to use z for standard normal random variables. The probability that z is less than, the z-scores, I guess I should put the z here, right? It's a z-axis. The probability that z is less than negative 0.84, okay, is about, I should put the squiggles technically, but pretend those are squiggles. That's about 0.20. Maybe I should do this. 0.20. And I'll put the squiggles in independently. Right. So the probability that z is less than negative 0.84 is about 0.20. Right. So if I throw a dart and it lands somewhere inside here, there's a 20% chance it lands in here. All right. Any questions? By the way, you might try this out. Try to go to tutorhomework.com. See if you can get this on tutorhomework.com or Excel. All right, 19.3. All right. If x has a uniform distribution on 5 to 15, find the probability that x is between 12 and 14. Okay. Now, I didn't require you to draw a picture, but it might be helpful, right? Visually. Not to scale, but let's see, this is 5, this is 15. Right. Uniform. So we get a rectangle of some sort. And then we're interested in values of x between 12 and 14, that in red. All right. So find the probability that if a dart gets thrown in here, it lands inside this bar here. All right. Now you didn't have to draw the picture. Okay. It really comes down to that formula, which I showed you earlier, right? That this probability equals x sub 2 minus x sub 1. This is the formula from the notes. You don't have to recopy it, but do show me the numbers you plug in. X sub 2 minus x sub 1 over b minus a. That's the formula that you would use. This is a. This is b. This is x sub 1. This is x sub 2. Think proportions. What's the proportion of this to all of this? All right. X sub 2 is 14 minus x sub 1 is 12 all over. B is 15. A is 5. All right. So 2 over 10. Yeah. So yeah, that's a big theme today. 2 over 10. I'll accept that. Remember, I don't require you to reduce fractions, but you should recognize that that's 0.2. It makes sense because it looks like there's only a small proportion of the whole. All right. So if you know how to do 3, then you can figure out 4. I'll leave 4 to you. Any questions? It's good that you you looked ahead. It's good that you actually looked at the problems. No, because I didn't specify. Okay, so if I don't specify a format, you could write it as a fraction, a decimal, or a percent. If there's rounding that could be involved, I'll tell you how to round off. Oh yes, I understand the issue of rounding, so that if I wanted something in decimal rounded off, I'd let you know. When in doubt, exact fractions tend to be preferable because it's easier to write things exactly using fractions, right? And usually it's more work to go to the decimal. You got to use a calculator or something. All right. You're welcome. Yes. So we're entering a new phase, right? Continuous probability. So you're kind of altering your mindset. Right. We're approaching 9:30. Any questions? You're very welcome. Yes. Again, if you forgot to turn in the homework, please turn in the homework as soon as possible. All right. So we ended early today, but I didn't think anyone was in the mood, either you or I, to start the next lesson. It's like, you know what? Let's calm down. We'll do some homework. Let's do some homework. Right. Okay, but I don't want to waste your money. So it's 9:30. Our class ends at 9:35. I'll keep the window open. Okay. Okay. Go for it. Yeah, no penalty. Go for it. Not that I could penalize anyone anyway, but all right. I'll stick around. I'll leave the window open. So if you have any questions here, if you want to do homework, right? Like maybe some on 20. I like to leave 4 to you because we did 3, but okay. If you want to work 20. Right. Okay. Otherwise, if there's nothing until 9:35.